Dark openings may very well be one of the generally captivating and baffling peculiarities in the universe. They are enormous monsters regarding power, yet at the same time, they are essentially imperceptible to us. A dark opening weighing maybe 2 to 4 times the mass of the Sun is a great representation of the exploration that has been placed into them over the last few years. We've gone from knowing literally nothing about them to discovering increasingly more. Recently, Kaku declared that we finally got to check what's inside a dark opening. This new data brings light to the subtleties the universe of science could have missed from the start. Join us as we dig deeper into dark openings and disclose what's inside. Space is huge and terrible. Before we dive into the details of what Kaku found, we need to discuss the first. Although most of us have some idea of what dark openings are, there are still some gaps in the correct information. You see, in 1916, Albert Einstein published his hypothesis of general relativity, which predicted the presence of dark openings. At that time, the idea was merely hypothetical. It required an additional 50 years for the scientific community to find proof that dark openings actually exist. This occurred in the 1960s when they were studying the Cygnus X1, a celestial body, and observed a strangely dazzling blue star emitting X-rays. This star was not a stale object but was circling around a giant dark something. Upon further examination, it was observed that the X-rays were not just moving around alone but were being sucked into the dark object they were orbiting. Accordingly, the name dark opening was given. This revelation was critical because it provided confirmation that dark openings indeed exist and were not just a fantasy of Albert Einstein's wild imagination. While that was extraordinary, it also meant that there was this stunning substance in space that we critically needed to know more about. Analysts worldwide got to work. This dark opening was named Cygnus X1, and it is situated in the constellation Cygnus, about 6,000 light-years from Earth. It was no small revelation. It's multiple times more brilliant than the Sun and incredibly dense, which gives it a strong gravitational pull. The gravitational force is so strong that not even light can escape from it. This is why it is known as a dark opening. The idea of a dark opening is both entrancing and terrifying. It is an area of space where gravity is so intense that nothing, not even light, can escape. Whatever gets too close to a dark opening will be sucked in and never seen again. However, that aspect of peril makes it significantly more important to learn all there is to know about them. Was this it? Or were we just beginning? The answer turned out to be the latter. After the discovery of Cygnus X1, researchers began to look for other dark openings. They found that there might be more than 100 million dark openings in the Milky Way alone, but since they are so staggeringly difficult to recognize, we still do not have a definitive number. All things considered, there are a few million dark openings in our very own galaxy, which makes them significantly more essential to study. So how about we break it down? The principal concern with dark openings is always going to be gravity. Their gravitational draw is so serious that anything that enters it packs down cosmically until it turns into a singularity. In simpler terms, dark openings resemble enormous vacuum cleaners that suck everything in. One of the most terrifying aspects of the research into dark openings is the reality that if someone were to fall into one, they would reach a point where they become a solitary line. This process would happen gradually, and the individual would die before the final structure actually sets in. So, let's just say that nobody ought to step into one. However, they're everywhere. So, might we truly be in danger? Regardless of the fact that the nearest dark opening to Earth is 500 to 1,000 light-years away, it's still close enough to raise questions and concerns. In 2021, researchers were able to deliver the first clear photo of a dark opening. Specifically, the M87 dark opening. This dark opening was photographed over several nights, and with each photo, the specialists gathered more and more proof about it. They had to combine the individual photographs together to create something that filled all the gaps. This way, they were able to figure out that there are 3 layers to a dark opening. It's not merely one single expanding hole of nothingness, as many individuals believe. Things are significantly more complicated than that. To even get to the nothingness part of a dark opening, you must pass through the initial 2 layers. The first layer is known as the event horizon, which is the final turning point. Once you pass the event horizon, there's no turning back, and you will be sucked into the dark opening. It just deteriorates from that point onward. The second layer is the photon sphere, which is the region where light orbits the dark opening. Any light that enters this region will be captured and cannot escape the dark opening's gravitational pull. Finally, we come to the third layer, which is the singularity. This is where all that enters the dark opening gets compressed to an infinitely small point. The singularity is a point in space-time where the laws of physics as we know them break down, and we can't predict what happens next. At the singularity, the density is infinite, and the laws of physics as we understand them cease to exist. Now, what makes all of this vastly more complex is that each dark opening you study will be entirely different from the last. Sure, they do tend to follow the same three-layer concept, but the way they function could be vastly different. Now, if this were anything more, all we want to do is bounce back on those telescopes and just concentrate on the main pressing issue exhaustively. Yet, with dark openings, you can't really do that. Researchers can study dark openings indirectly by observing the radiation they produce and the gas and dust that surrounds them. Sending a probe, like the Voyager, inside a dark opening isn't feasible because anything that enters the event horizon is pulled toward the singularity, where it is compressed to an infinitely small point. So, you can't exactly waste billions of dollars just to get an impression each time, because the second the probe gets close enough, it will simply be crushed into nothingness. Due to that very obvious issue, researchers are left with no choice but to study these objects in a two-dimensional manner, even though they are three-layered singularities. To make matters even more challenging, there are also the two issues of each dark opening being unique and the laws of physics as we know them breaking down when we attempt to investigate the inside. This means that the conventional methods of scientific inquiry don't really apply to the study of dark openings. That doesn't mean the analysts haven't been busy. There are numerous theories and explanations about dark openings, and with each one, things get increasingly more fascinating. One of the most compelling theories about the formation of dark openings is that they are made from collapsing stars. When a star exhausts all its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. Thus, the star begins to collapse in on itself, becoming denser. If the star is massive enough, this process can continue until it turns into a singularity. To understand the nature of dark openings more deeply, NASA researchers directed their focus toward the center of the universe, M87. Cosmologists observed a massive whirlpool of extremely hot hydrogen gas that was rotating at an astonishing pace of 1.2 million miles per hour. The sheer power of the rotating plate of gas should have caused it to fly apart in all directions, but it didn't. Researchers deduced that there must be a massive object concentrated at the center of the galaxy to prevent this from occurring. This enormous item weighed as much as 2 to 3 billion suns and must be a dark opening. But that is not the only hypothesis regarding dark openings. In 1963, New Zealand mathematician Roy Kerr utilized Einstein's equations of gravity to provide the best description of a rotating dark opening. He showed that a rotating dark opening wouldn't collapse into a point, as previously thought, but instead into a ring of fire or a thin circle. The circle would rotate so quickly that centrifugal forces would prevent it from collapsing. This rotating circle of matter is known as the ergosphere, and it is the region surrounding the dark opening where the laws of physics begin to break down. The most fascinating element of Kerr's solution was that it predicted the presence of an Einstein-Rosen bridge, also known as a wormhole. This hypothetical tunnel through space-time could connect two separate areas of the universe or even two parallel universes. The idea is that if one were to fall into a dark opening, rather than being crushed to oblivion, one could be sucked down a tunnel through the ring and shot out a white hole in a parallel universe. To grasp how this works, we need to look at the concept of spacetime in Einstein's theory. Spacetime is the fabric of the universe, where objects with mass warp this fabric, creating a gravitational field that causes other objects to move toward them. Now, imagine a piece of paper representing spacetime. If you place 2 points on the paper and define a line between them, this is a depiction of how objects travel through spacetime. But what if you could fold the paper and create a shortcut between the 2 points? This is the fundamental idea behind a wormhole, a shortcut through spacetime that connects two distant points in an instant. Wormholes aren't just a science fiction concept. They are actually a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse almost immediately. However, the existence of an Einstein-Rosen bridge would imply that dark openings are not merely enormous vacuum cleaners, but could also serve as gateways to different regions of space-time. So could we use a wormhole to traverse space and time? Unfortunately, the answer is likely no. Not yet, anyway. Even if we could stabilize a wormhole, it's unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit on how fast anything can move through space-time. Still, the concept of wormholes and dark openings as pathways to other parts of the universe or even to different times has been a subject of interest and theory among physicists for a long time. The possibility that there may be shortcuts through the fabric of space-time allowing travel over vast distances or even into the past could be revolutionary if we could indeed achieve it. One of the most captivating ideas in this area of study is the Kerr wormhole, named after the mathematician Roy Kerr, who first described it using Einstein's equations of gravity. This type of wormhole is essentially a theoretical passage through space-time that could connect two distant points, such as two different universes or even two different times within the same universe. The Kerr wormhole is often imagined as a ring-shaped portal, much like the mirror in the tale of Alice in Wonderland. Walking through the looking glass transported Alice to a realm where creatures spoke in riddles, and logic didn't always apply. Similarly, traversing the Kerr ring could potentially transport a traveler to another universe or some other time where the laws of physics might be very different from those we are familiar with. Yet, while the possibility of wormholes for the purpose of interstellar travel or time travel is undoubtedly exciting, it is also a subject of debate and discussion among physicists. Some have pointed out that wormholes, especially traversable wormholes, may be unstable or difficult to navigate due to the intense radiation and subatomic forces surrounding their entry. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and dark openings, only apply to gravitational forces and not to the quantum forces governing radiation and subatomic particles. To truly understand the nature of these phenomena, another theory is needed to unify the laws of gravity with a quantum theory of radiation throughout the universe. This is known as a theory of everything, a single theory that can integrate both Einstein's theory of gravity and quantum mechanics. One prominent theoretical physicist who has been working on a theory of everything for a long time is Edward Witten, although there are numerous variations of what this could entail. The one that has shown promise is superstring theory. Superstring theory combines gravity with a theory of radiation. It suggests that subatomic particles are actually tiny vibrating strings and that the universe is an orchestra of these strings. Just as different musical notes correspond to various vibrations of a violin string, different particles in nature relate to different vibrations of a superstring. One of the fascinating aspects of superstring theory is that as a string moves through time, it distorts the fabric of space around it, creating dark openings, wormholes, and other intriguing arrangements predicted by Einstein's equations. This means that superstring theory not only unifies Einstein's theory of gravity with quantum mechanics, but also explains many of the strange phenomena we observe in the universe. However, there's something about this theory that complicates its simplicity. In a way, it makes more sense, too. Superstring theory requires 10 dimensions of spacetime in which the strings can vibrate. This is vastly different from the 3 dimensions of space and 1 dimension of time that we experience in our daily lives. It's hard to imagine what these additional dimensions might be like, but physicists have developed some applied models to help us understand. Consider a 2-dimensional lake inhabited by fish that are only aware of the dimensions of length and width. To these fish, there is no such thing as depth, and they can't even conceive of what it would be like to live in a 3-dimensional world.